So let me talk a little bit more about masking MCDC. That may have not been entirely clear from the previous recording that I made. So for example, if you look at Z equals A or B and C or D, like you see in this particular Boolean expression or decision, what you can do too, you can realize that if you write C or D as a proxy variable, say Y, then this can also be written as E or B and Y. Well, in this case, you see that if you look at test cases 2, 3, and 4, and you would express the expression as A or B and Y, then you can see you can combine 2, 3, and 4 as the same test case. Why? Because, even though C and D are changing, the C or D, in order to proxy variable Y, is not changing. Yeah? So that means that's very nice because this gives you more possibilities. Now you can say, well, 2 can be combined with 10 like we had before in unique cause, but 2 can also be combined with 11 or 2 with 12. So masking MCDC gives you more opportunities to come up with test cases. So in the other example that I gave you, where I did this strong condition coupling, in which case you have two conditions that are the same, A and B, or not A and C, which represented this particular variable. In this case I said, well, if I assume A and B as a proxy variable X, then I can also write this as X or not A and C. So X plus not A and C. So if I do that, then now I can say, well, if I have this case 2, I can also have case 6 and 10. They're the same because, X is F, A is F, and C is T, and that's the case for these two. Of course, you realize that X is a proxy variable, but since A and B gives you F for FF, FT, and TF, the use of proxy variable is allowed. In this case, you see both for the A equals F case and the A equals T case, you'll have multiple combinations. I can combine 2 with 4, or 2 with 8, or 2 with 12. Yeah. So these more combinations are good because now you can get rid of also the cases that you can't use. Remember, if A is false, like in this particular case, case 4, A is false and A is true, that of course can never happen. You cannot do the test and set it up such that A is both false and true at the same time. So in this case you can say I'm removing these test cases that I can do, in which the A in the first part, A and B, and the A in the second part, not A and C, are different. So I got rid of those, and it means you can see which cases are left over. And so it's very simple. Like that also means that the black ones are the only cases that are left over. Okay, so that's what we do. I try to make it a little bit more clear. Hopefully it is. If not, feel free to send me any specific questions. So let's now look at typical Boolean decisions. So I told you before, if we have a particular Boolean expression, for example, this expression has an AND operation, A and B, and not A and C, and then an OR operation. So it's A and B, or not A and C. Yeah, so what are we going to do for each of these Boolean decisions? Suppose we have an AND gate. Yeah, if we have an n input AND gate, to get test cases that satisfy MCDC, you're going to set all the inputs to true. That's one test. And then you're going to take each and every input and set it exclusively to false. Yeah. So for example, in this case, I'm going to take the case in which A and B are both true. That would be a test case, so that's true, true. But I'm also then going to say A is false, B is true. And I'm going to set B false, and so A is true and B is false. I'm getting true, true, false, true, true, false would be my test cases. Yeah? So true, true, false, true, true, false. So for any input so n input AND gate, this is what you're doing. So for the 3 input AND gate, for example, if you have A, B, C as an input to this AND gate, you say I'm going to first set them all to true, and then I'm going to set each and every input exclusively to false. So in this case, I'm setting A to false and the other two to true. Then I'm setting B to false and A and C to true. And in the last case, I'm setting C to false and A and B to true. So these 4 test cases will give you MCDC, so modified condition decision coverage, for a AND gate decision. Now an OR gate, oops, let's go to the next slide. An OR gate is kind of similar, but in this case the test cases include first setting all the inputs to false, and then set each and every input exclusively to true. Because remember, in an OR gate you can only get false as an output result if all the inputs are false. If one of them is true, one or more is true, then the output of this decision is true too. So you need to include the test case in which all inputs are set to false. So again, if you look at the 2 input case, I'm setting all of them to false. A is false, B is false, and then I set each and every input exclusively to true. So A is true, B is false, A is false, B is true. Okay. So for a 3 input OR gate, I'm getting true, false, 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 true, false, 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 true, and false, false, false. Now if you have an exclusive OR gate, you can actually get this. You have multiple options you can take, but you have to, so how do you get that? You get that from solving this very simple truth table in a way similar to what we did earlier in either masking or unique cause MCDC. Actually, we need this one. Yeah. So in that case, see that there's multiple sets of test sets possible. You can combine 1, 2, and 3, 1, 2, and 4, 1, 2, and 5, and 2, 3, and 4. In all cases, of course, there's 2 inputs, so 2 conditions in this case, so that means that you have 2 plus 1 equal to 3 test cases that are required. In case of a NOT gate, you set a true, a false. So it's more or less the same as extensively testing this one. Okay, so if you have decisions, like comparisons, what you're going to do in these particular cases, in this case you have one condition. You're going to say A is larger than a particular value. Yeah. Then what you need to do, and this includes less than, greater than, less or equal than, greater than or equal to. So in this case you want to set the input slightly above the comparison point, slightly below, and equal to the comparison point. So what you're really adding in this particular case is the robustness test cases. And of course, you want to make sure that this is either true or false. So in this particular case, I'm saying x is larger than 2500. So if you would take this as a single, this is a single condition. It needs to be true and false. So I could pick 25 for it to be false, 32,000 for it to be true, and then in this case I add the robustness test cases. So these would be better choices. So I'm going to write exactly at 2500 and then slightly below, slightly above. So these 3 cases would be just sufficient. If then else, what you want to do, the minimum set of cases are inputs that force the execution path to then and to else, and of course everything that you need for the decision logic. While loops, really same as we saw with the if-then statement. Now, so what you typically do, one method, and this method is given in this document that's provided to you on Blackboard. It's a practical tutorial modified condition decision coverage by Kelly Hayhurst and a couple of others. And what you're doing is, one way to do this, you create a schematic representation of the source code. You identify the test inputs that you used. You eliminate the masked test cases. And then, based on the resulting, you say if MCDC is achieved. Okay, now suppose we have the following example. So suppose we're evaluating a power management system that has two generators. There's two failure flags, one for generator 1, one for generator 2. And there's also a requirement to set a flag to shed partial load to start electrical load shedding in the event of a single generator failure. So we're going to share the load, and another flag if both generators fail. Okay, now the person that took this requirement and developed 3 test cases. It says both generators have failed, and let's fail both generators and check out if shed partial load is false and shed full load is true. In other cases we fail generator 1 and keep generator 2 up and running and make sure that shed partial load is true and shed full load is false. So these are the outcomes that should be based on this requirement. Test 3 would be fail the second generator and keep the first one valid. In that case, shed partial load should be true and shed full load is false. Now, suppose that somebody in their source code actually implement the following logic. They said, okay, to make this work, I'm taking these 2 flags, and to get the shed partial load, I'm taking the OR operation of both, and to shed the full load, I'm taking the AND operation of both of these flags. So if you take that code and then perform step 1 in order to turn it into a schematic representation, you see I'm first taking the exclusive OR between those 2, and then I'm actually taking the AND operation between inputs also. So exclusive OR, AND operation. Exclusive OR, AND. So then in steps 2, I'm going to put the test cases at the beginning of those that I would need. Yeah. So what you see in this particular case, I have 3 cases. So in this case, both are failed. So test case 1 would be both flags failed are true. Both are failed, so it means the flag is going to be true. In the second case, you failed generator 1, so that's going to be true. And the second one is going to be false. And the third one, you failed generator 2, and the first one is working, so you can say false for the first one, and the first one is working. And it generated 2 fail flags, as okay, then that's not working. Okay, so in this case, I'm actually working out the AND operation. So in this case, it's going to be true, false, false out here, and exclusive OR gives you false, true, true. In this case, there's no test cases that are masked because no gate outputs are input to other gates. There's no masking going on. It only happens when there's the output of one gate goes to the input of another gate, like we saw before. So determine Mcdc. You're just going to say, okay, let's take this parameter here, exclusive OR. From the earlier logic here, we found out we need to have at least these kind of test cases. So if I do that, I need at least true, 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 false, and false, true. And you see I got those. These are included. True, 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 false, false, true. So I'm looking at my earlier statements, my earlier block diagrams to find out what cases I really need. And I'm going to check out if the cases that are seen in this diagram are truly there. So in the AND gate, I say, well, I need to have all of them true. And then I need to make exclusive each of the inputs false. And you see I got those as well, so there's none missing. So in this case, we're good to go. Our test cases were sufficient for Mcdc, and so the source code is good. It covers Mcdc. Now, another way you could implement this is actually by taking, that somebody would take this requirement that we had before and implement the source code just slightly different. Again, he took generator full load, generator 1 fail, and generator 2 fail, but now somebody actually implements this exclusive OR differently. It has generator 1 fail or generator 2 fail and not shed full load. And of course, if you work that out, shed full load would be the AND. This turns into, if you do the Boolean reduction, this will turn into A exclusive OR B. Like we had before, it's just a different source code implementation. Well, in this case, it's a little more complicated because now the AND gate here goes into another gate, goes into another gate. So now masking could occur. Okay? So if you look at this particular case here, you again have the same cases that we saw here. It's going to be again true, 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 false, false, true, because the test cases were already decided. But now what you're seeing is, now there is, if you look at test case 1, yeah, you know, in test case 1 results, in test case 1, the output here becomes true, becomes false. So this case here has no consequence. No matter what happens over here, it's going to be ignored because there is a fail in. There's always going to be failed. So there's masking going on. Yeah? This failure causes masking. So test 1 is eliminated due to masking. So to make this thing work with this particular source code, if I look at the AND gates, you see I reduced one test case here for this OR gate. So that means that I no longer, and this AND gate, so I no longer for the second AND and second OR have the 3 test cases that I would require. So in this case I need to add true false, and for the OR gate I need to add false false. And then you get complete coverage.